Hello, viewers. Waiting for a few more people to join. All right. Cool. Hope everyone's doing well today. I have a song stuck in my head, which is the Evil Morty theme from Rick and Morty. Do you guys know that one? The evil, because there's Evil Morty. It's been stuck in my head for the last few days. All right, well, nice to see you. Or, well, I guess I'm not seeing you, but I will see you later on. It's been about a week since I last taught you guys live. And so we had a pre-recorded lesson on Tuesday. That pre-recorded lesson was purely qualitative, so there were no numbers involved in that lesson, and so for that reason there was no quiz for that. I can't remember if I said that or not, but there's no quiz for that. The quiz for this week is for this lesson that we're about to do right now. So what is this lesson about? Well, we are going to talk about simple harmonic motion graphs. Okay? And so we'll start off just by drawing a position time graph. So I have a position time graph, and I'm going to draw one full period of the position time graph. So that is a full period. Okay? And so, again, a full period means you go forward and you go back and you come back to where you started. All right? The graph wiggles between the two extreme points. So here's x equals 0. And the most positive the x value goes is an amplitude. And the most negative it goes is minus an amplitude. Okay? And so that's supposed to be level with that. So what we want to do is we want to produce a bunch of other graphs from this. And so to do that, we're going to need a couple of formulas, which I will write up here. You already learned all of these formulas. There's the period of a mass spring system. By the way, this is all pertaining to the mass spring system, which is 2 pi square root of m over k. we learned an equation for the maximum velocity when you're undergoing simple harmonic motion, which is square root of k over m times the amplitude. So just to remind you, k is the stiffness of the spring, m is the mass that's going back and forth, the amount of mass, and capital A is the amplitude. We also learned an equation for the maximum acceleration, which is k over m times a with no square root. And we learned a couple of equations for the energy, but we're only going to use two of them. One of the formulas for energy comes from evaluating the energy at the extreme point. And at the extreme point, the energy is entirely elastic potential. So when we did that, we got an equation for the energy, which was 1/2 Ka squared. And then the other place where we could evaluate the energy was at the equilibrium point, or as it goes through the equilibrium. And at that point, it only has kinetic energy. So the energy could also be thought of as 1/2 mv max squared. These two are going to give the same answer because simple harmonic motion is an exchange between elastic potential energy and kinetic energy. So the energy starts out all in one form, and then it shifts back and forth. Okay, and at one moment it's all going to be kinetic, and at a later moment it's all going to be potential, and then it's all going to be kinetic, and then it's all going to be potential, and it just sloshes around back and forth. Okay, so these two are equal to each other. And so these are relatively new equations, and I just want to remind you guys that the velocity is the slope of the position time graph. Okay, so these are some factoids from way back in the beginning of the school year. And then the acceleration is the slope of the velocity time graph. Okay? So we're going to use all of this information to help us get more graphs, starting with this. Okay? So the first thing I'm going to do is I'm going to draw the velocity time graph. And so I like to draw the velocity time graph directly below the position time graph so that I can make the times line up. Okay? So the first thing we want to do is we want to get the general shape of the graph. Okay? So what is this graph going to look like? Well, we're going to use the fact that the velocity is the slope of a position time graph. So I'm going to pick 5 points. So I'm going to break a full period up into 4 segments. And those 4 segments are separated by 5 points. And then I'm going to look at the slope at each of those 5 points. Okay? So at this time, I can see that the slope is positive. Okay? So you want to imagine that you're a skier, and if you were skiing on that slope, which way would your skis point? Here your skis are pointing uphill. That's a positive slope. So at the same time in my velocity graph, I'm going to mark a positive value. See, it's above 0. Here, at this point, I can see that the slope is 0. All right, if you were skiing on this slope, your skis would be horizontal. So at that time, I'm going to mark the velocity as 0. Here at this time, I can see that the slope is negative. So I'm going to mark a negative value for the velocity at that time. Here I can see that the slope is 0 again, so at that time I will mark 0. And here I can see, at this point, I can see that the slope is positive, so I'm going to mark a positive value at that time. So what I have are, I looked at 5 points across a, yes, derivatives. This is a much easier lesson if you know about derivatives, but this is not a calculus-based class. I am going to circle back to that thought towards the end of the lesson, though. So now what I'm going to do is I'm going to take all of these points and I'm going to connect them by a nice smooth curve. Like that. So now I have the general shape of the graph. Okay? So that's step 1, is you get the general shape of the graph, not worrying about the exact numbers. Then what we have to do is we have to figure out, well, what does the velocity wiggle between? So what are the values that it wiggles between? And to do that, we go to our equations. And I know that the velocity's biggest value is going to be V max, which is square root of k over m times the amplitude. So that means that this graph is wiggling between square root of k over m times the amplitude and minus square root of k over m times the amplitude. Okay? So we use the previous graph to kind of get the slope, or the general shape, and then we use the equation to get the maximum and minimum values. The next graph we're going to make is the acceleration time graph. So again, I like to draw that below the velocity time graph. Why? Because acceleration is the slope of the velocity time graph. So I'm going to do the exact same thing, only this time I have the velocity graph that I'm looking at the slope of. Okay? So again, I have 5 points marked, and I'm going to look at the sign of the slope. Not the value of the slope, just the sign. Here, the slope is 0. So at that time, I will mark 0 for the acceleration. At this time, the slope is negative, so I will mark a negative value at that time. At this time, the slope is 0, so I will mark a 0 value at that time on the acceleration graph. Here, the slope is positive, so I will mark a positive value on my graph at that time. And here, the slope is 0, so I will mark 0. So now I have 5 dots, which I can use as a basis to sketch the acceleration versus time. So it's going to look something like this. All right. Now what we want to do is we want to figure out, what does this graph wiggle between. Okay. And so to do that, we go to our equations. In particular, I have an equation for the maximum acceleration. It's k over m times the amplitude. So that means that my acceleration is going to go between plus k over m times the amplitude and minus k over m times the amplitude. All right? So that is the first part. There's actually 3 more graphs that we are going to make. The first graph I like to draw next to the position graph, and that is the potential energy versus time. And I want the period to be the same. So let me just mark this, and then so right here is 1 period, and we're going to graph the elastic potential energy as a function of time. Now, one of the things to remember is that elastic potential energy is 1/2 kx squared. So notice how it takes my position graph and it squares it. Okay, so what I'm going to do is I'm going to take these same 5 points and I'm going to connect them, and I'm going to square each of these values. Okay, so if I square 0, I get 0. So at this time, I'm going to mark 0 as the potential energy. Here I have a positive position. When I square a positive number, it is still positive. So at that time, I will mark a positive number for the potential energy. Here, halfway through the period, the position is 0. So when I square 0, I get 0. So my potential energy will be 0. Okay. Here I have a negative value, so here's where you can get mixed up. When you square a negative value, it becomes positive. So my potential energy at that time is going to be positive, even though the position is negative. So I marked a positive point at that time. And then lastly, I have a position of 0, so when I square 0, I will get 0. So again, I have 5 points, which I can use as the basis for sketching out the potential energy as a function of time. One of the things that I want you guys to notice is that see how the potential energy graph actually wiggles twice as fast. So whereas my position graph goes up and down in a full period, the potential energy goes up and down actually in half a period. So we get 2 maxima in the same amount of time for the potential energy graph. Why is that? It's because you have the most potential energy when you're at plus A, and then you also have full potential energy when you're located at minus A. So you, in a single period, you get to full potential energy 2 times. So you get 2 bumps. All right, so that is an important point that's going to show up in your quiz for today. So what does the potential energy wiggle between? It wiggles between 0 and the full amount of energy, because simple harmonic motion is an exchange where all of the energy goes potential and then it shifts to all of it being kinetic. So I could actually use either of these formulas. I could say that the maximum is 1/2 Ka squared, or I could say that the maximum is going to be 1/2 mv max squared, because those will both give the same number. All right. The next graph I'm going to draw is the kinetic energy as a function of time. All right. And so kinetic energy is 1/2 mv squared. So notice how I square the velocity. So that's why I'm drawing the kinetic energy next to the velocity, because I know I'm going to square this graph. So I'm going to take my same 5 points, okay, 1, 2, 3, 4, 5, and I'm going to square these velocity values and look at the sign, okay? So here I have a positive velocity, so when I square it, it is still positive. Here I have a 0 velocity, so when I square it, it is still 0. Here I have a negative velocity. When I square a negative number, it becomes positive. Here I have a 0 value, so when I square it, it becomes 0. Here I have a positive velocity, so when I square it, it will still be positive. So I have my 5 points, which I can use to connect the dots. Again, I see the same pattern where here I have one valley, but for the kinetic energy graph in a full period, I have 2 valleys. All right, and that is because in a period, you swing through equilibrium multiple times, right? If you're going back and forth, equilibrium is in the middle. Okay, so you go through equilibrium once when you're going back, and you go through equilibrium again when you're going forth. So you get 2 maxima of the kinetic energy in a single period. So this graph is going to wiggle between 0 and the full amount of energy, because simple harmonic motion, the energy goes all kinetic and then it goes all potential. So the maximum value of this graph is 1/2 mv max squared. Or we could write it as 1/2 k a squared. Okay? You cannot have negative elastic potential energy or negative kinetic energy. That's another reason, yeah. So now the last graph we're going to learn how to draw today is the total energy versus time. And that's the easiest one of them all, okay? Because the total energy is kinetic plus potential, and it's a constant. So constant graphs are flat, right? They have no slope because they're not changing as time goes on. So this is going to be your energy versus total energy versus time graph. And the value is, remember, the energy goes all potential at one point. So that is 1/2 k a squared. All right? And this is assuming no friction, because in Tuesday's lesson we actually drew this graph, but we drew it as decaying to 0 because friction will take the total energy and dissipate it into heat. But we are back to the situation of a frictionless mass spring system. Okay? Another interesting way, so you could just say that, energy is constant, so it has to be flat. But we could actually imagine adding these two graphs together. And one of the things that's interesting is when the potential energy has a peak, at the same time the kinetic energy is having a valley. And similarly, when the potential energy has a valley, the kinetic energy at the same time has a peak. Okay, so basically when we add these two together, the kinetic energy is going to fill in when the potential energy is low so that they combine to make a steady, constant value. One of the things I want to point out, a common mistake, if we were going to have an actual in-person exam, I would have you sketch out these graphs. And one of the things that I see oftentimes when students are drawing are connecting the dots, like on this one, for example. Sometimes they draw it with a cusp. And when I say a cusp, I mean like a sharp point here, but it's not like that, okay? It actually smooths out. It does this. So just be aware of that. This is the correct drawing. You don't draw a cusp or a point here. So I'm just going to have a brief interlude where I talk a little bit about calculus. So calculus is not required to take AP Physics 1, but there's just a good connection here, so I want to talk about it briefly for about 4 minutes. Okay? So bear with me if you're not in calculus. What we can see here is that your position is essentially a sine graph in this case. All right? So my position is behaving like sine. All right? Now, if I want my velocity, I have to take the derivative of the position with respect to time. And taking the derivative of sine gives cosine. So the velocity graph should look like cosine. And indeed, that is the case here. This is the same as a cosine graph because it starts high and it goes down from there. The acceleration is the derivative of the velocity. So we have to take the derivative of cosine, which is going to give us negative sine. All right, and indeed, our acceleration time graph, it starts out at 0 and it goes down from there. So that's the graph of negative sine. So that's nice. To get our potential energy graph, well, that's going to be 1/2 kx squared. And so we're basically going to take this position and we're going to square it. So the position, so the potential energy time graph is going to look like a graph of sine squared. So if you've ever typed in y equals sine squared of x in your calculator, you know what it looks like, and it looks exactly like this. All right, so that's nice. If we want to make our kinetic energy versus time graph, well, kinetic energy is 1/2 mv squared. So I have to square the cosine. So our kinetic energy graph is going to look like cosine squared. All right. And indeed, this is the graph of cosine squared. Now, this is probably my favorite one. If we look at the energy, the total amount of energy is kinetic plus potential. All right. And the kinetic is acting like cosine squared. The potential is acting like sine squared. So the total energy behaves like cosine squared plus sine squared. And if you know from your math class, cosine squared plus sine squared is equal to 1, which is a constant. So basically, you know, we can go through all of the business of using conservation of energy and using slopes to sketch out the graph. Or if you know calculus, it's a little bit quicker because you just take derivatives and you square things and it all works out exactly the same. All right? So what we're going to do now is we're just going to do one concrete example with actual numbers, okay? Just to see how that works. So here's an example, and this example is going to have a 3 kilogram mass. So in other words, that is oscillating, so that you're given that piece of information. And so I will draw the position as a function of time. because I'm talking about a concrete example where I'm actually using numbers, I put units on the axes. When I was going over this before, I was just talking conceptually about graphs. And so in that case, I don't have to put units. So I just have position, time without units. But when you are talking about a concrete problem with actual numbers that are representing reality, you need to put units on there. And so here is the graph. I'm going to draw some guidelines to help me. So let's see, that, like that. All right, well, that's a pretty good graph. Okay, so this is going to be 0.4 seconds, and this graph is wiggling between plus 0.5 and minus 0.5 meters. Okay, so from this graph, we can immediately get a little bit of information. Okay, first of all, we see that the period is 0.4 seconds. All right, we see that the amplitude is 0.5 meters. And of course, we know that the mass is 3 kilograms. All right, so we're going to use these three pieces of information to allow us to actually calculate these maxima and minima for all the other graphs. Okay, so we're going to be using these equations to get actual numbers for all this stuff. So at this point, I like to do a little sidebar calculation. All right. So in particular, the period of the mass spring system is 2 pi square root of m over k. All right. So I know that the period is 0.4 seconds equals 2 pi square root of the mass, which is 3, over k. So stiffness of the spring was not given. And I'm going to need that in the subsequent formulas. So I better start off by calculating the stiffness. So I hope you don't mind. I'm not going to show the algebra. And I already did this last class period, so I'm just going to say what the solution is. So you work this out, you solve for k, and you get that the stiffness is 740 newtons per meter. Okay. So now I'm going to calculate Vmax. Vmax is square root of k over m times the amplitude. So notice how to calculate Vmax, I needed to know the stiffness. So that is why I calculated the stiffness first. So I have square root of 740 divided by 3 times the amplitude, which is 0.5. And you work that out, you get that the maximum speed is 7.9 meters per second. We're also going to need the maximum acceleration, which is k over m times the amplitude. K is 740, m is 3, amplitude is 0.5. So this gives a maximum acceleration of 123 meters per second squared. And then lastly, we're going to calculate the energy, which is, there are multiple formulas. We could use 1/2 mv max squared. So that would be 1/2 times 3 times 7.9 squared. Or we could use 1/2 Ka squared. Those will both give the same answer, and you can check that for yourself. 1/2 times 740 times the amplitude, which is 0.5. So as a sanity check, these both have to give the same answer, which I assure you that they do. And that value is 92.5 joules is the energy of this vibration right here. So now we go about and we make the graphs. Oh, one other point I wanted to make is that not every position time graph has to be, quote, a sine graph, all right? So here, our position time was represented by a sine. Here, it's not a sine, it's actually a negative cosine graph. This is negative cosine, because yeah. So, but we go through the same procedure, all right? If I want the velocity as a function of time, again, I'm putting units on the axes as well. I take my 5 points and I look at the slope at each of those 5 points. And at the corresponding times, I mark the sign as positive, negative, or 0. Here, I have a slope of 0, so I'm going to mark 0 at that time. Here, I have a positive slope, so I will mark a positive value at that time. Here I have a 0 slope, so I will mark 0 at that time. Here I have a negative slope, so I will mark a negative value at that time. And here I have a slope of 0, so I will mark a 0 slope there. So I have all my dots, which I can then use to connect. All right, so now I have the general shape, and now I have to figure out what does it wiggle between, and I already did that calculation because I found that Vmax is 7.9, so we're going to use that number, and the velocity wiggles between plus 7.9 and minus 7.9 meters per second. All right, let's go to the acceleration time graph. So again, that's going to be the slope of my velocity graph. Putting units on the axes, Putting units on the axes, acceleration is in meters per second squared. So taking my 5 points, and getting the sign of the velocity. So here I have a positive slope, so that means I have a positive acceleration. Here I have a 0 slope, so that means I have a 0 acceleration. Here I have a negative slope, so I have a negative acceleration. Here I have a 0 slope, so I have a 0 acceleration. And here I have a positive slope, so I have a positive acceleration. All right, I've got my 5 dots, so I connect them. Like that. And the last step is to figure out what do they wiggle between. And I calculated the maximum acceleration right here, so that's going to be what the values wiggle between. So plus 123 and minus 123. So we've got 3 more graphs to go, and then we'll be done. The next graph is the potential energy in joules versus time in seconds. Here's 0.4 seconds, the period, and then I divide it up into 4 parts. So again, we want to square this graph to get the shape. So squaring this negative number will give me a positive. At this time, squaring 0 will give me 0. Here, squaring a positive number will give me a positive number. Squaring 0 will give me 0. And squaring a negative number will give me a positive number. So I have my 5 points, which I then connect with a nice smooth curve. Remember, don't put cusps in there. The potential energy wiggles between 0 and the total amount of energy, which is 92.5. All right. So then we get the kinetic energy graph. And I'm going to do this one in a different way from what I did before. So we could square your velocity graph. But another way you could do it is if you already have the potential energy graph, you notice that, remember, whenever the potential energy is high, the kinetic energy is low. All right, so here if the potential energy is high, my kinetic energy is going to be low. Here my potential energy is low, so my kinetic energy is going to be high. Here my potential energy is high, so the kinetic is going to be low. Here the potential is low, so the kinetic will be high. And here the potential is high, so the kinetic is low. So I can get the 5 points that way as well. Connect them with a nice smooth curve. And then again, it wiggles between 0 and the total amount of energy, which is 92.5. The last graph is your graph of total energy versus time. Which is the easiest graph of them all because it is simply a flat graph. Again, we're not worrying about friction like we did in Tuesday's lesson, so the energy is constant, and the value of that constant energy is 92.5. All right, so that is my lesson for today, and I will see you in the Zoom room.